welcome everyone. Today is the lecture of solution of week 7 assignment. In the previous lecture of summary of week 7, we have talked about, we have summarized whatever we have covered in this week 7. Then we have also discussed about the assignment, which is we discussed about, we can read about time series analysis and then stationary and non-stationary approaches. No, time series analysis, why it is important? When we are talking about climate extremes, we have to observe either from the observed data set or some sort of model data set, or let us say some sort of remote sensing based data set. From the observed data set, let us say you have a river and there is a river, you have one particular station, and from that particular station you are recording the water discharge data daily. Let us say you have taken the maximum value for each different years, and that is represented by Q max. So, let us say you have 40 years of daily data set. For each individual year you have taken the maximum value, that is the peak value of flow for individual years. Let us say you have 40 years, then you have 40 peak values of flood in a one particular location. So, for each corresponding maximum value you have time series year, and that you can do that, and then you can plot it like that. For example, this is, let us say we can make a plot. So, let us say this is time, and let us say this is, you are plotting Q max. Q max is the maximum value of runoff you are calculating for different years, that is the maximum value. That is also the block maxima approach. So, it can be something like this as well, or maybe if you plot it, it can be, this is time, or it can be your year, and then you have Q max. So, it can be something like this also, or maybe if you are doing this analysis, it can be something like this also, which is basically continuously decreasing. So, probably it is like this or slightly above. So, this is maybe we can say more or less it is consistent trend, and this is basically kind of increasing trend of Q max, and this is we call say decreasing trend of Q max. All of these are sort of time series data set. Now, using these time series data set, you can infer that at what period of time or what location in a one particular basin or one point or one location, the peak flows or the climate extremes or hydroclimate extremes are continuously rising. How do we know that rising? That maximum has been breached by another maximum, another maximum, another maxima, like that. So, that is basically we can say that this is a continuously rising. It is also possible sometimes, sometimes your flow is somewhere like that and something happened and then your flow is something like that. So, this is your original conditions, this is your transformed conditions. So, this is also says that there is something happened to, let us say a river or flow which has completely transformed the whole time series behavior of the dataset. So there could be many reasons like this or like this or like this or like this. There could be many reasons of happening all these different types of time series behaviors. So the time series analysis is a very useful tool which can give you an idea about how you can use all these information to look at what is the frequency of occurrences of these different extreme events, how what is the rate of increment of these extreme events, how these different types of extreme events are rising, or which period of time we have observed a significant increment in the time series magnitude of now let us say different types of climate extremes. Okay. So, yeah. So, why it is important? So, let us say if you are planning for some sort of uh, early warning system or some sort of hydrological structure or some sort of hydroclimatic control structure, something like that, and you have this much amount of time series data set, but let us say the economical value of your project is lies more than that, more than your time series data, then in that case this serves as a historical period of record where we understand the trend, we understand the frequencies or probabilities of extreme climatic events, or maybe we can talk about their magnitudes. And then using this particular information you can project it for the remaining or the future time step, or project it for future steps, so that we can identify what is the likelihood of different maximum event or peak event and what is their magnitudes, whether a particular structures can survive the magnitude of those different climatic extremes at that particular period or time. So, what is the time series basically? Let us say this is your hydroclimatic data set, this is your time. So, let us say I am taking any peak value, okay, and this is basically a kind of a pattern here like this. So, this is basically called a time series data set. Here you can take, let us say this is your mean value, and this is the fluctuations around the mean value. So, sometimes you have higher values, sometimes you have lower values, sometimes you have much higher, very higher values like that. So, this is basically you can calculate, this is your mean value and this is fluctuation around that mean of the data set. In the mathematical terms, basically you can, let us say if you are referring this time series as xt, where it is basically x1, x2, x3 till xt, that represents y1, y2, y3, yt like that, years. This is years, this is your hydroclimatic extremes. So basically, so this is basically we can use it. So we can you can use it, these terminologies, to define our time series data set. Time series can be represented by two component. One is called deterministic component, the another is called random component. So this is basically called the deterministic component, and this is we called the random component. So if you are looking at this particular time series data set, what would be the deterministic component? The mean value, because we can determine it, we can calculate it, and there is a fluctuation around the mean value is your random fluctuations. So suppose mathematically, if this is xt, dt and epsilon t, let us say, you can calculate dt, that is your mean value, and if you can model these random fluctuations around the mean with certain models, you would be essentially can predict your xt value for at least historical period, and then you can use it for your future time steps as well. So now there is another few examples where we can also further talk about what are different case studies where we can use that deterministic components like that. So suppose this is your another let us say extreme time series data, and here it is something like this, it is continuously increasing. So here when we writing the xt and this is dt and epsilon t, so this deterministic is basically the trend or positive slope of your data, and then this epsilon t is the random fluctuations around that particular trend. Or let us say you can take another example of, let us say, decreasing trend. So here this is basically your decreasing trend, there would be negative slope, and that is would be your sort of deterministic component, and the random fluctuations around that is your the random component of your data set. So one thing you are sure about, what is deterministic component, what is your random component. This is another case study example. You can take xt t, let us say there is something like this and something happened and this is something like this. So in this scenario, so there was a, let us say, mean 1, that is called mean 2, and there is a difference in mean 1 and mean 2. So that is basically the difference in this particular can act as a deterministic component, or maybe if you are interested in modeling this part, that would be the mean of your deterministic, and if you are interested in this part, that would be your part of your deterministic component. But when you are talking about this, this can be your deterministic component, and around that fluctuations you can think about, that is your random fluctuation around the. So this is all about time series data set. So another part of this assignment was, how do we define a particular time series is stationary or non-stationary. First we will let us understand the concept of stationary. Suppose this is your data set okay, and this is your, let's say, xt, and this is your time. So this is a mean of your data, let's say mu, mean basically represented by mu symbol, and this is sigma is represented by standard deviation. So this is, let's say, mu, and let's say you break the data into several parts, let's say 3 parts, first, second and third, and you can plot this data into different figure. This is the first part, let's say this is xt, this is t, then the second part of the data t, and the third part of the data. Okay. Now you can also calculate what is the mean mu1, mu2. Let's say you can calculate what is the mu2, and you can also calculate what is the mu3. Suppose mu1 is equal to mu2 is equal to mu3. There is no significant changes. In that condition, we say that the deterministic component of your all these time series are consistent, and therefore there is no change in the mean behavior of the time series. Similarly, you can also by the way, how do we calculate mu? Mu is calculated by let's say you have x1, x2, x1 plus x2, let's say you have xn data, and you divide by number of time series, that you will get mu value. You can also calculate standard deviation by similar type of formula. For example, the standard deviation can be defined by sigma is equal to xi minus mu square divided by n. So here xi is the value at each different points, mu is the mean, and n is the number of length of your data set. So it is also possible that, let's say, there is a mean like this, then in the another series like this, and then another series like this. So if you look at this, then you cannot say that mu1, mu2 and mu3, probably mu1 and mu3 are equal, but mu1 is not equal to mu2 and mu2 is not equal to mu3. Similarly, if you talk about another time series where the fluctuations were like this, but suddenly the fluctuations were like this, then fluctuation was like this, like that. So here in this part, your sigma 1 will be different, here sigma 2 will be different, sigma 3 might be same or different. So maybe sigma 1 is equal to sigma 3, but sigma 1 is not equal to sigma 2, because there is a change in the variability of the system, or sigma 2 is not equal to sigma 3. Okay, so this is what it is suggesting, that let's say if your statistical properties so let's say mu, sigma, skewness, kurtosis, etc. is remained same if you are taking different set of the data set data, that we call a stationary condition, which means there is no significant change we observed in the data set. But let's say if there is a change in the statistical behavior or if it is mu1 is not equal to mu2, or sigma 1 is equal to not equal to sigma 2, or skewness is not equal to skew2, like that, or kurtosis is not equal to 1 and 2, it is possible that you can refer that this is basically a kind of non-stationary conditions. So, in the previous example we talked about the data set which has a trend, a jump, those types of data sets are non-stationary. When we do not have any kind of trend and jump, or is a random fluctuations around the mean, that can be considered as a stationary, given the fact that if the mu1, mu2, mu3 are equal or no significant differences, or let us say sigma 1, sigma 2, sigma 3 are almost equal, or there is a no significant difference we observed in the data set. So, that is the definition of stationary and non-stationary, and I hope I have also covered some basic area of this time series analysis. I hope you have understood the very general concept of time series, how we can apply it for climate extremes data set, and you can calculate various different statistical properties to understand that whether the particular time series is stationary or non-stationary. That would be useful for your climate extreme analysis. Thank you so much for this particular lecture.